In the last lecture we had seen that if for a planar waveguide V is less than pi by 2, then the number of modes is 1, it supports only one mode, and when V lies between pi by 2 and pi, there are two modes, and if it is between pi and 3 pi by 2, then there are 3 modes, and so on. If I keep on increasing the value of V, then the number of modes would increase, but what I also see that the propagation constants can be approximated by certain expression, and we can find out the propagation constants even without solving the transcendental equation for first few modes. So, let us see how. So, if it is a highly multimode waveguide where V is much larger than 1, typically if V is more than 10 or so, then what I see, if I now again plot these transcendental equations, this is eta is equal to xi tan xi, and the blue one is eta is equal to minus xi cot xi. Now, if I plot the sections of circles for large values of V, let us say V is equal to 10 or V is equal to 18 or 20, what do I see that for the first few modes the points of cross sections are somewhere here. So, for first mode, that is m is equal to 0 mode, the point of intersection is close to pi by 2, and for m is equal to 1, the point of intersection is close to pi, and so on. So, and these are only for first few modes. If you go to higher order modes, then these points of intersections are much farther from these values. So, what I can say that for first few modes, the points of intersections can be given by xi m is equal to m plus 1 pi by 2, where m is equal to 0, 1 or 2. So, for m is equal to 0, it is pi by 2, for m is equal to 1, it is pi, and so on. So, in this case I can find out the beta in this way. I know xi m is equal to kappa m d by 2. So, it is equal to m plus 1 pi by 2, and kappa m is k naught square n 1 square minus beta m square root. So, this gives me beta m square is equal to k naught square n 1 square minus m plus 1 square pi square by d square. Now, I can increase the value of V by two ways. I can have large value of V by two ways. One is that if I have very large value of D, if I have large value of D, then you can see that these beta m will approach to k naught n 1, beta m will approach to k naught n 1, and it is obvious. It is if I start from a very thin waveguide, then there are discrete modes and they have propagation constants which lie between k naught n 2 and k naught n 1, but when I increase this width of the waveguide, and the width is very large as compared to lambda, then it is as good as infinitely extended medium. So, the light will propagate with propagation constant k naught n 1, where n 1 is the refractive index of the medium. So, I will approach towards infinitely extended medium if D is very large. Now, if I obtain the large value of V by having very large index contrast, that is very large difference between n 1 and n 2, then what happens is there is a huge index contrast, and this very large index contrast will give very high reflection, okay, very high reflection. Okay. So, it would be difficult for the wave to penetrate into N2 region. So, it would be something like, it would be very close to what is planar mirror waveguide, and in that case you can see the expression for these beta closely resemble to the expression of beta for planar mirror waveguide. Let us work out some more examples here. Okay. I consider a Stepindex planar symmetric waveguide with n1 is equal to 1.5, n2 is equal to 1.4 and d is equal to 4 micrometer, and let us calculate the number of modes at 0.5 micrometer and effective refractive indices or effective index of modes of TE0 and TE1 modes. So, again, to find out the number of modes, it is the same, I find out the value of V. So, when I find out the value of V, it comes out to be 13.53 at lambda naught is equal to 0.5 micrometer. If I divide this value of V by pi by 2, this number comes out to be 8.61. So, the number of modes supported would be 9. Okay. I can see this value of V is very large. So, it would be now easier for me to find out the propagation constants of TE0 and TE1 mode even without solving the transcendental equation, since it is much larger than 1. So, for the first few modes the values of beta would be given by this, and for TE0 mode m is equal to 0 and for TE1 mode m is equal to 1, and in this way if I find out the values of beta, then they come out to be 18.83 and 18.78. Correspondingly, the effective index of TE0 mode comes out to be 1.498698 and for TE1 mode 1.494783. You can see they are very close to the refractive index of the guiding film, which is 1.5. Okay, now let us do extend all this analysis by using normalized parameters. So, we had symmetric modes, anti-symmetric modes, and the transcendental equations were in terms of xi and v. Okay. Now, I already have one normalized parameter, which is normalized frequency V, which contains all the waveguide parameters and wavelength. Let me also define normalized propagation constant, that is, let me normalize beta. And how do I normalize beta? That I take beta over k naught square minus n2 square divided by n1 square minus n2 square. If I normalize beta in this way, then for guided modes the value of B lies between 0 and 1. So, for guided modes the value of B lies between 0 and 1. So, this is now normalized propagation constant. Now, my task is to replace that xi with B and V. So, how do I do this? So, this is the transcendental equation for symmetric mode, this is the transcendental equation for anti-symmetric mode. Okay. Let me find out how can I get xi in terms of B and V. So, xi square is equal to kappa square d square by 4. So, this is nothing but d square by 4 and kappa square is k naught square n1 square minus beta square. I do a little mathematical manipulation, I add and subtract k naught square n2 square here, and then I regroup these two terms and these two terms. So, if I group these two terms and these, and also I take this term outside. Why I am doing so? Because I can immediately identify that if I club this term with this, I get V square. Okay. So, I do that. So, this becomes xi square is equal to k naught square d square by 4 n1 square minus n2 square times 1, and from here I take minus outside and I write it down as beta over k naught square minus n2 square divided by n1 square minus n2 square. So, this is nothing but B. So, this is B, this is V square. So what I have got now from here, xi square is equal to V square, and this is 1 minus B. Okay. So this gives me xi is equal to V times square root 1 minus B. So as soon as I get this xi in terms of V and B, I put it in these equations and I get the transcendental equation in terms of B and V only. So for symmetric mode, this transcendental equation will transform to V times square root 1 minus B, tan V square root of 1 minus B is equal to V times square root of B. Okay. Because from here V square minus xi square, V square minus xi square would be V times square root of B. And for anti-symmetric mode, this equation will become this. Okay. From here I can find out the cutoff condition of a mode. Okay. A mode is said to be cut off when its propagation constant approaches k naught n2. I know that if n effective for guided modes, I know for guided modes n effective or beta over k naught or n effective lies between n2 and n1. So if this beta over k naught approaches n2, then a particular mode is cut off. So a mode is guided when the effective index of the mode lies between these two, but as soon as the effective index goes below this, then it is no more guided. Okay. So this value of n effective will give me the cutoff. Okay. This beta over k naught is equal to n2 gives me B is equal to 0. So this is the cutoff condition in terms of B. So from here I can immediately find out for what values of V, for what values of normalized frequency a mode would be cut off. So I simply put B is equal to 0 here, then the solutions of the equation that I get will give me the cutoffs of the modes. So this will give me, if I put V is equal to 0, sorry, B is equal to 0 and V is equal to Vc, which symbolizes the cutoff frequency, cutoff normalized frequency, then it gives me Vc tan Vc is equal to 0 for symmetric modes, and for anti-symmetric modes it will be Vc cot Vc is equal to 0. So these two together will give me the cutoff of mth mode as m pi by 2, where m is equal to 0, 1, 2 and so on. So TE0 mode will have no cutoff, m is equal to 0. TE1 mode will have a cutoff of pi by 2, TE2 mode will have cutoff pi and so on. So this is how I get the cutoffs of the modes. Now a very beautiful thing about these normalized parameters is that they are independent of waveguide parameters. I get these two equations and these two are purely mathematical equations, two purely mathematical transcendental equations. What I can do, I can solve these equations for different values of V, okay, and I find out the roots of these and plot these roots as a function of V. So I start with a very small value of V. Okay. When I do this, as long as the value of V is less than pi by 2, then what I see that there is no root coming out from this equation and there is only one root coming out of this equation. Okay. I find out that root for different values of V and plot it. It goes something like this. As soon as the value of V crosses pi by 2, one root starts appearing from this equation, and the value of V up to pi, I will get one root from here, one root from here. I keep plotting them, okay, and then I further increase more and more roots start appearing and I plot them. Okay. The very first root which comes from here, which is closer to 1. Okay. The first root which is closer to 1 is TE0 mode. The first root from here is TE1 mode. The second root from here is TE2 mode, and so on. So, I plot them. Once I have plotted them, then these curves are universal curves. So, once I have done this exercise, then it is forever. These are universal curves. Now, what I can do using these curves? Okay. If there is a given waveguide and wavelength, then I simply calculate the value of V. This should be V, not, and there should not be any 0 here. So, I just calculate the value of V, and then I go to these curves, okay, and read the value of B corresponding to that value of B. For example, if I get this value of V, let us say V is equal to 1.4, then I draw a vertical line corresponding to V is equal to 1.4 and read the value of B corresponding to this from BV curves. Once I get the value of B, then I can find out the effective index of the mode from here. This is coming out from the very definition of the normalized propagation constant. If I am somewhere here, if the value of V is, let us say, 3.5, so it will go like this. I will have 3 points of intersection, and corresponding to that I can read the value of B. So, I will get the propagation constants of all the 3 modes. So, in this way I can find out the propagation constants for any symmetric planar waveguide. Let us do some examples. So, if I have a waveguide with N1 is equal to 1.5, N2 is equal to 1.48, D is equal to 2 micrometer, and I operate it at lambda naught is equal to 1.5 micrometer. If I calculate the value of V from here, it comes out to be 1.0226. I go back to those BV curves and read the value of B from here corresponding to this value of V, it comes out to be 0.4636, and then I find out the value of N effective, which comes out to be 1.4893053. Okay. Now, I change my waveguide parameters a little. Okay. So, I now have N1 is equal to 1.5, N2 I have changed to 1.418, D to 1 micrometer, and lambda naught is equal to 1.5. I have artificially changed these parameters for achieving the same value of V actually. What I want to demonstrate is that if my waveguide is different, even if my waveguide is different, but it gives the same value of V, then the value of B is always the same. For same value of V, even if the waveguide is different, the value of B, normalized propagation constant, is the same, but the effective index would be different now, because N1 and N2 are different. So, in this case the effective index is this, while in this case the effective index would be this. Okay. So, different waveguides can have same value of V and hence the same value of B, okay, which means that these B V curves are universal and they do not depend upon waveguide parameters. Let us now look at modal fields. How do the modal fields look like? Okay. Let us plot the field for TE0 mode. Okay. TE0 is symmetric mode. So, the modal field will be given by Ey of x is equal to A cosine kappa x in the region mod x less than d by 2, and C e to the power minus gamma mod x for mod x greater than d by 2. Okay. I know for TE0 mode xi would lie between 0 and pi by 2, okay, because V would lie between 0 and pi by 2. So, the point of intersection, the value of xi for point of intersection will always lie between 0 and pi by 2, it will not exceed pi by 2. What is xi? Xi is kappa d by 2. So, kappa d by 2 will lie between 0 and pi by 2. Now, let us look at the waveguide and the modal field. In the region mod x less than d by 2, the solution is cosine function. Okay. So, I will have cosine kappa x. Okay. What would be the value at the boundary? What would be the value at the boundary? At the boundary, I have kappa x is equal to kappa d by 2 and minus kappa d by 2. Okay. But kappa d by 2 is always less than pi by 2. If kappa d by 2 is always less than pi by 2, then cosine kappa d by 2 will never cross any 0. Okay. The first 0 of cosine function will occur at kappa x is equal to pi by 2. Okay. But I have even at the boundary kappa x is always less than pi by 2. So, I will not have any 0 crossing. So, E y in the guiding film will be like this. Okay. And then in the lower refractive index region, the exponentially decaying part, exponentially decaying solution will take over and it will go like this. So, I will have the modal field which would look like this. All right. What I see that there is oscillatory solution here and decaying solution here. The field extends to lower index region also. How much does this extend into this region? Okay, I can quantify this. Okay, I find that at x is equal to d by 2 plus 1 over gamma. Okay, because this field is going as e to the power minus gamma times x. So, at x is equal to 1 over gamma, this field will decay to 1 over e of its value at the boundary. So, if I start from here and move a distance 1 over gamma from the boundary, then the field will decay to 1 over e of its value at the boundary. Then this is how I can quantify this distance up to which this field extends into the lower index region. So, it is defined by 1 over gamma, okay, and it is known as penetration depth into lower index region. So, 1 over gamma is penetration depth into lower index region. Let us plot the field now for TE1 mode. Okay. TE1 mode is antisymmetric mode and the solutions would be given by sine function in the guiding film and exponentially decaying function again in the lower index medium. Now, for TE1 mode, xi would lie between pi by 2 and pi. Xi would lie between pi by 2 and pi, because the green curve will cut the blue curve only in this region. Okay. Now, which means that kappa d by 2 would lie between pi by 2 and pi, and now in the same way if I plot the field in the guiding film first, so there would be a sine function. Okay, but at the boundary it has to be less than pi. So, kappa d by 2 has to be less than pi. So, it would not cross another 0, there would only be one 0 which is at x is equal to 0. Okay. So, in the guiding film the solution would be like this, and in the lower index region the exponentially decaying term will take over, and this is how the modal field would look like. Okay. So, I can see that if I go back, then here for TE0 mode there was no 0 in the modal field, there was no 0 crossing. For TE1 mode there is only one 0 crossing, and if I go on, then TE2 mode has 2 0 crossings, TE3 mode has 3 0 crossings, which means that if it is TEM mode, then it will have m number of zeros, okay. It will have m 0 crossings, okay. This is one thing. Another thing that I see is when I solve this, okay, that with the number of modes the propagation constant decreases, right. If you remember the B V curves, so you have, this is V which is normalized frequency, this is B which is normalized propagation constant, and B always lies between 0 and 1 for guided modes. I had seen that TE0 mode goes something like this. This is TE0 mode. TE1 mode, it goes something like this. This is TE1. TE2 mode like this. So if I have a value of V somewhere here, then the propagation constant of TE0 mode is here, propagation constant of TE1 mode is here, propagation constant of TE2 mode is here. So, the propagation constant decreases as the mode number increases. I also see that the lower order modes are more confined into guiding film. So, you can see that TE0 mode, it has more power here, and as I and the tail into N2 region is smaller, but as I go to higher order modes, this tail extends more and more. So if the number of mode increases, if the number of mode increases, then the corresponding confinement in the core decreases, okay. I can see the effect of this penetration depth, I can see this penetration depth, okay. So, for a given waveguide, if beta decreases, because penetration depth is defined by 1 over gamma, and gamma is equal to beta square minus k naught square and 2 square, it's a square root. So, if beta decreases, then if beta decreases, then gamma decreases, which means penetration depth increases, and beta decreases with mode number, okay. So, that is why the penetration depth increases. So, if I have this waveguide and this wavelength, and I see the mode profiles of different modes. So, this is TE0 mode, it has penetration depth which is about 0.47 micrometer. For TE1 mode, this is 0.52 micrometer, and for TE2 mode it is 0.65 micrometer. What is the effect of index contrast on penetration depth? Well, again, the penetration depth is given by this. So, for a given N1, D and lambda naught, now if I change the value of N2 and hence the index contrast. So, for example, if I decrease N2, then the value of V increases, because N1 square minus N2 square increases. If V increases, the propagation constant, increases, beta increases, if beta increases, gamma increases, and penetration depth decreases. So, this is how it looks like. So, if I have N2 is equal to 1.48, then penetration depth is 0.47 micrometer for TE0 mode. For the same mode, if I change the refractive index N2 from 1.48 to 1.3, then you can see the penetration depth decreases, the field is pushed more towards the the guiding film, and if I change to 1, then it is even more confined into the high index region and penetration depth decreases to 0.1. What is the effect of wavelength? If for a given waveguide, if I decrease the wavelength, then I am increasing the value of V, which means I am increasing the value of propagation constant. Okay. If I am increasing the value of B, that is beta square minus k naught square n2 square increases, gamma increases, so penetration depth decreases. So, this is the field of a given waveguide when operated at 1.55 micrometer. You can see how much the field extends outside, and when I decrease the wavelength to 1.3, the field is pushed more towards N1 region, and when it is 0.7 micrometer, then the penetration depth is much smaller. So, this is how the modal field would vary with different parameters of the waveguide and wavelength. In the next lecture, we will have more insight into the modes, and we will understand what these modes basically are. Okay. We will have physical understanding of modes. Thank you.